Hi, welcome to es301 Engineering Analysis. This is chapter 13 on one-dimensional unconstrained optimization. So here are the learning goals. At the end of this video, you'll know the difference between constrained and unconstrained optimization. You'll know the efficiency benefits of the golden section search method. You'll understand how the parabolic interpolation method works and how to implement it. And you'll understand how Newton's method works for functions for which the derivatives can be calculated. So first, I want to go ahead and discuss the golden section search. And in general here, what we're looking for is optimization. So what we're trying to find is where a function is a maximum. So for example, if this is my one-dimensional function, what I'm looking for is that point right up there at the top. I want to go ahead and find out where it's a maximum. This is very similar to root finding, and we'll find actually when we look at Newton's method, we're actually just going to be doing effectively root finding. Now, one thing about the golden section search is that you need to know where your optimum occurs. And so here I'm going to have some lower bound, call that x sub l, and some upper band up here, I'll call that x sub upper. And so I know that the maximum is going to be somewhere in between those two functions there. And so effectively what I would need to do in order to find out where that maximum is, I need to go ahead and evaluate at two other points. So maybe at that point and that point right there. I might kind of just make these evenly spaced. And then what I'm going to do is I'm going to look at what the function value is at those 4 points. So I'm going to go ahead and evaluate it at those points. And then what I'm going to do is I'm going to throw away one of these sections. Now notice I need to have 2 points because, for example, if I didn't have the left one, I just evaluated the function here, here, and here, I wouldn't know which side of the function to go ahead and throw out. But here, what I would notice is that this value here, let's go ahead and just call this value over here. I'll call this x sub 2 and this x sub 1. At this point, I'll realize that x sub 2, f of x sub 2 is less than f of x sub 1. And so what that means is I'm going to clearly want to go ahead and throw away, for example, that section right over there because I know the optimum is going to be over in between here. And then I'm going to go ahead and find, for example, a new 4th point and go ahead and evaluate it there. Right? Now, what would be the choice of these points? And as I mentioned, maybe we'll go ahead and evenly space it. One of the problems with evenly spacing them is that if I keep going down here and now I throw away this section here, this little section starts getting smaller and smaller if my optimum tends to be just over the minimum. And so maybe there's a little more efficient way to go and determine how to divide those sections instead of doing it evenly spaced. And so what I could do is use what's called the golden section search, where here I'm going to go ahead and I have my lower bound on the left and my upper bound on the right. This is a figure from the textbook. And then my 2 points that I'm going to go ahead and pick right over there are actually going to have this relationship where if I call the distance between lower and upper L naught, and then I go ahead and call the distance, for example, between the lower and this farther point L1 and what remains L2, is that we have L1 over L0 is going to equal to L2 over L1, right? And so it's just got this particular relationship. And if I do that, I find that that actually equals 61%. So let me go ahead and kind of wrote on there. That distance right over there is about 61.803, and that's called the golden ratio. And there's a reason why this tends to be somewhat efficient. And the reason that it tends to be somewhat efficient is that, for example, let's go ahead and look if we evaluated at these points. I'll come back to this diagram here. If we were to go ahead and evaluate our function there, we're now going to go ahead and throw away the section on the right. But now we only need to go ahead and evaluate at one more point because we're already going to have the attribute, if we pick a point over here, where we're still going to go ahead and satisfy that ratio. And what we're throwing away each time is 39% of the whole function, so we're narrowing in very quickly. Whereas over here, if I evenly divided it, I was just throwing away 33.3% of the function. All right. Now, what would be this particular value? How do I go and determine this 61.803%? This is actually what the function is. This is from the textbook. They use the symbol D. The symbol D is just this value of L1 that I indicate right over here. Square root of 5 minus 1 over 2 times that distance. And so this number right over here is the 61.803%, and that's what's known as the golden ratio. And this is why this is called the golden section search. And then I can go and determine what my 2 points are. This is x1 on the right, and this is x2 on the left. And x1 is going to be x lower plus d, so I'm going to come over to there. And then x sub 2 is x upper minus d. And so just be a little careful there. Notice that x1 is to the right of x2, and so we're kind of determining that larger value at those 2 points. Let me return. I forgot to mention, what do we mean by unconstrained search? And what we mean by unconstrained is that we're not putting any constraints on what the value of x is. X should go anywhere from negative infinity, be less than x, then positive infinity. So we're not putting any constraints on what the value of x is. Later on chapters, we'll look at constrained optimization, where we might be trying to find the optimum of x in some particular region. And that matters when you have the difference between, for example, a global maximum and a local maximum, which means, for example, if I had a function that looks like this right over here might be my global maximum, but if I was constraining my system to look only in here, this right over here would be my maximum because I'm constrained in here. But we're looking at unconstrained optimization. So all we're going to need to know is that we're between 2 points that we're looking for. One last thing let me mention is how to determine what the error is in the golden section search. And here's an equation from the textbook where this 1 minus r value right over here, this is r, this 61.8%. And then it's times the difference between xl minus x upper over x op. Let me explain what that is. Okay, so for example, let's go back up to my picture in the diagram here. And say we went over here and we evaluated at x1 and x2. We went ahead and threw away this right-hand side. And now we want to go ahead and determine what my error is, okay? Well, we know that our optimum is somewhere in this region right over here, somewhere to the left of x1 or to the right of x1 up to, of x2 up to x1 from x lower. And so this right over here is my unknown region, and so that's going to be a measure of what my approximate error is. And so this function, a little bit of algebra, if you look in the textbook, results in this equation here, where x opt is the value of x that you didn't throw away. So in this case, it would be the value of x2. If we've thrown away the left-hand side, it would be the value of x1. And that kind of comes in important when you do the very last homework problem this week. Okay. Now you might wonder, why do we care about doing something very, very efficiently? It seems like, who cares if we were throwing away 39% or 33%? And let me mention practical applications. And so one practical application is actually related to facial recognition. And maybe you've noticed this is like the login screen. And on Windows 10, for example, if you have a camera on your computer or your laptop, instead of typing your password, it actually looks for you. It turns on the camera and looks to figure out if you are the person using it. It actually works pretty well, and it's kind of nice. You don't type your password every time that you log in. If for some reason you turned on your computer and were looking sideways, or maybe you weren't in front of your computer, you might have seen this message where it says, can't recognize you because it wasn't able to find you with your camera. And what it's doing is image recognition. And the way image recognition works is effectively what's called one method is called image segmentation, where it takes a picture. So for example, to the left here, we take this picture, and then what we're going to do is try to break it into particular parts. And what you end up doing is a series of optimizations throughout this image. And so you go through various types of optimization, coming into different types of segmentation as you move across to the right. And so you have something that the computer can go ahead and determine essentially, yes, that's the person, or no, it's not. And the amount of optimization that goes in this multi-dimensional picture with multiple colors is actually pretty image intensive. And when you log in, you don't want to wait, 5 minutes for it to determine if it's you. You like that it happens in a split second. And so that's where we actually do a lot of optimization. So it matters if you're throwing away 33% or 39% in terms of the optimization. So I know in these examples in textbook, it seems sort of simple because we're doing nice little one-dimensional optimization. And so maybe it takes 9 steps instead of 10, but it matters if it takes 900,000 steps instead of 1 million steps. All right, let me talk about 2 other methods in addition to the golden search, and one is called parabolic interpolation. And so, as I said, there's a lot of analogies between optimization and root finding. So let's go back to root finding. Remember, if we had some sort of function, we were trying to find the root there between upper and lower bound. Well, one thing we could do is we could take 2 points and draw a straight line through it. Well, what we could do instead when we're doing optimization is do something similar, where now what I have is a function, and I know that it's bounded somewhere between 2 points. We'll call that x lower and this x upper. And what I'm going to go ahead and do is just take some point in the middle, maybe that point right there. And then what I'm going to do is, once I have 3 points, I can go ahead and fit a parabola to it. And so I'm going to fit a parabola to those 3 points there find the maximum of my parabola, which would be right at that point, and this is going to be my new guess of where my optimum is. And then what I'm going to do is go ahead and throw away again to the left or the right. In this case, what I'm going to realize is that since this point here is greater than that point right there, I'm going to throw away the left-hand side, and I'm going to go ahead and use those 3 points and draw a new parabola through there. And so this is going to be another way to go ahead and do optimization. It's similar, the end goal is the same as the golden section search. So if this point over on the left, I'm going to call that x0, and the one on the right, x1, and the one in the middle, x2, to stick with the notation in the book. What I need to do is find this new point, which is the middle of that parabola. A whole lot of algebra comes up with this equation right here, which you get from the textbook for the value of x3. All you need to be able to do is evaluate your function at the points. So left is x0, right is x1, the middle is x2, and you can go ahead and determine your value of x3. Now, one of the things you need to do each time is determine which section to throw away. And first of all, it's going to kind of depend on whether x3 right over here is greater than or less than x2, and then you're going to be looking at whether its function value is greater than or less than x2. So there's 4 different situations that you need to evaluate of whether you want to throw away the left-hand side or the right-hand side. Okay. Each time, if you want to determine the error, what you're looking at is this value right over here, so effectively x2 over x3, and then you're going to be normalizing that by x3. So my approximate error is going to be x2 minus x3 over x3. And what you realize each time is that this value of x3 becomes the next value, x2. So eventually you're looking at it from the previous point. So it's very similar to types of approximate error that we have done before in the past. All right, let me talk about one last method. This is Newton's method. And again, this is very similar to root finding. So let me just remind you, in root finding, if I was trying to find the zero of a function, in Newton's method, I only needed 1 point, and then I was able to take the derivative. So I needed to be able to take the derivative of the function, projected it down to the axis right over there, and this was my new guess. And that's what we do in Newton's method. So what we're going to do is run something similar now, because I've got a function I'm trying to find the maximum of. And so one of the things to remember is that if I've got a maximum or a minimum, the derivative is 0. And so at this point right over there, if this was the derivative of the function, that right over there would be the same point. So if this is my function f of x, this one right over here, I could call g of x, which is just the derivative of the function of x. And now I'm finding the 0 of g of x. So then I'm going to go ahead and just use Newton's method. So if I go ahead and plug that in, I end up with this equation. You might recognize similar to Newton's method, except now I have a first derivative in the top and a second derivative in the bottom, because what I've done is I've substituted in f prime at x to be, I'm trying to find the 0 of g of x. And so then I go ahead and just iterate each time through here. Now, one of the things you might notice with Newton's method, I need to be able to find both the first derivative and the second derivative. The second derivative has to be non-zero in order to go ahead and find the maximum of it. So this works well for analytic functions. The other thing with Newton's method, remember this is an open method, which means that it's not bounded. I'm not dictating an upper and lower bound, and one of the problems with that could be non-convergence. And so, for example, if this is my function here, f of x, and I'm trying to find the maximum or minimum of it, well, I've got 1 right there, I've got a minimum right there and right there. Newton's method will go ahead and find any of those points depending on where you're starting. So if this right down over here is g of x, which is just the derivative of f of x, and so right at this maximum I've got it at 0, this point 0, and this point 0. If I start looking in here, I'm going to go ahead and find my my maximum there. If I start looking down here, I might go ahead and start finding the minimum, but if I'm over on the right-hand side, I could go ahead and diverge, and it could be non-convergent. So you need to be a little bit careful with your function in order to make sure it converges, but when it doesn't converge, it tends to converge fairly quickly. All right, so let's review what we talked about in this video. First, we saw there's three unconstrained optimization finding methods. There's the golden section, the parabolic method, and Newton's method. Golden section maximizes efficiency, and that can matter in very data-intensive optimization routines. So again, I mentioned it seems a little simple in the homeworks that we do here, but it really matters in terms of image analysis, just to improve a few percent in terms of efficiency. Parabolic interpretation can be faster than golden section, but if one side gets hung up, it's actually a little bit slower. So sometimes there might be a mix between golden section and parabolic interpretation. In fact, that's what's known as Brent's method. Brent's method is a combination of the two. We didn't cover them here, but it's just effectively using golden section surf and parabolic interpolation, using one or the other. When you get hung up, you go to golden section, but maybe it was converging fast, you use parabolic. So it's just kind of a hybrid mix of the two. And lastly, we talked about Newton's method. It's a modification of the root finding method, but what it requires is an analytic function that you can go and determine two derivatives of. And finally, Newton's method is an open method. We only start with one point, find the derivatives there, and that has the caveat in that it can be non-convergent. Both golden section and parabolic will always converge, assuming that your upper and lower bound the minimum or the maximum that you're looking for. Let me also just reiterate, all of these, I keep mentioning finding maximums, they also find the minimums just as well.